Good morning, everyone. Delighted to see so many people here, particularly during the 2-week break. And this morning we have Jen Keenan to talk to us over from civil engineering. So I know, Jen, we've worked together on some simulation of aerodynamics around a bridge, which is great. It was a bridge in Ireland. And every time I drive over it now, I think of Jen. Like, oh, look, this is the Ireland bridge, which is great. She also survived being taught by me as an undergrad and still went on to do CFD, which I'm very impressed with. So for a few different reasons around the area, because my area is CFD as well, it's the research that I do. Slightly different backgrounds. I'm mechanical engineering. Jen is civil, but we'll put that beside us for today. So I'm looking forward to hearing what she has to say about aerodynamics and structures. Thanks, Jen.
Okay. I just realized, where should I stand from the, is here okay? Okay, perfect. So I'm going to talk a little bit about computational modeling of flows in the built environment. And I've deliberately chosen the word flow because it's broad in terms of, it could be a fluid, it could be a gas, it could be fire, it could be smoke, it could be anything that behaves as a flow. So this is a picture that I kind of also deliberately chose because it's a bridge, it's the Golden Gate Bridge. It's me in it for scale, so it kind of gives you a sense of the scales I'm talking about. In civil engineering, things, we're talking about large structures and objects. We're not talking about small things. And also that is the main cable. That's one of the main, the two main cables of the Golden Gate Bridge. It's very large. It's steel. And it doesn't look like it would move, but it very definitely moves. All bridges move quite a lot. So it's just to kind of give you a sense of some of the ideas, the themes that I'm going to talk about. So the buns, if you had any, the buns are homemade. That's the toddler making them last night, and the baby there watching. So do feel free to have a bun. I promised I was going to bring home baking, and I'm true to my word. Okay, so what I do. So as Connor mentioned, I do computer modeling, computer simulations of the equations of motions of fluids. So the fluid dynamics equations. And there's a number of applications that I focus on. So one of them is related to de-risking offshore renewable energy infrastructure. And renewable infrastructure is quite broad. It's everything from the cables to the turbines themselves, or the anchors of the turbines, the substations. Often we think about the turbine in isolation, but actually there's a whole electrical engineering infrastructure that's needed to manage the power, and so on. I also, it seems like quite a different application, but there's a lot of parallels. I look at bridge vehicle safety in high wind environments. So here the fluid is wind as opposed to water. Sorry, the flow is wind. So that's a picture there of the Tacoma Narrows bridge disaster. That was in the 1940s. And it's largely understood to have been caused by wind, not a particularly fast wind. And the motion of the wind interacting with the motion of the bridge was too much, and it collapsed. I'm also a little bit involved in using these modeling methods to optimize wastewater treatment processes, and also in eco-engineering sea defenses, and that's with Saladin, who's joined, who's sitting down the back. So I'm going to focus a little bit more on the bridge one today and the offshore one, as I'm a little bit more involved in those. So just for a little bit of context and to connect with the Earth Institute, these are the key themes, and I kind of fit into quite a number of these, as you'd imagine, from the variety of work that I'm involved with. So the built environment, obviously, water, climate, and sustainable communities, making sure that we have places that are pleasant to live. So a little bit more about the bridge vehicle safety in high winds. So the colorful rainbow style image there in the background, that's one created by one of my PhD students. And this is the object that's hidden behind the bridge. But it gives you a sense of the complex flow behavior that we don't see with our eyes, but that's happening around a bridge. And the challenge is that a windy environment, not necessarily extreme winds, interacts with the bridge, which in itself is always moving, which is carrying traffic, which is moving. And all of this dynamic interaction can cause quite dangerous conditions. And the challenges are around knowing when to close a bridge to traffic, or perhaps impose speed limits from the point of view of safety. So there's a couple of goals to my work in this space. There's obviously the applied research question around safety, bridge safety, vehicle safety, pedestrians, cyclists, and so on. There's also a very fundamental basic research question where the current accepted method of analyzing bridge vehicle safety is using wind tunnel testing. And that makes an assumption that the bridge is a line. It's a one-dimensional assumption. And that's a very massive assumption to make, given the modern computational capacity that we have and the numerical methods that we have. And there's also a really important policy piece to this work, because the bridge designers, the bridge operators, tell me they don't have guidelines on how to use numerical methods for analyzing bridge vehicle safety. And they don't have operational guidelines on when to keep a bridge open or when to close it because of extreme wind events. So where I'm at with all of this, so I have field data, which is fantastic, for two big bridges, one in Ireland that Connor mentioned, and one up in Scotland, the Queensferry Crossing. So these two bridges have been instrumented with thousands of sensors, and the operators have kindly shared that data with me. And that's brilliant for validating these numerical models. I've got meteorological input from Connor, so he's been able to look at the large-scale climate models and the weather forecasting models, and then give me input data for particular scenarios that I might be modeling. I'm connected with the stakeholders, like I mentioned, the designers of bridges, the operators. I use iCheck quite a lot for the computer processing. And I've started the conversation around policy with the NSAI, and that's a slow conversation. It's something that'll perhaps unfold over 5, 6, 7, 8 years. So the future in this space is that I've got lots of great ideas. I've got data. I've got models that have been started. But I would love more students. So I need more bodies to help me do this work. So that's a little bit of a kind of a call. And if you're interested in what I'm talking about here, I'd be delighted to connect with anyone. So the second piece then that I wanted to focus on is a little bit more on de-risking offshore renewable energy infrastructure. So sediment dynamics and seabed dynamics are not terribly well understood. It's a very active environment. There's a lot of dynamics involved, much like the wind bridge dynamics. And this is an image from Arklow Bank. It's the only wind turbine farm that we have off the Irish coast. And very soon after it was constructed, there were major scour issues identified and a lot of repair work done. So understandably, this has made developers very nervous. They're not going to pump billions of euros into putting up turbines if there's a fear that they might be washed away. So the goal is to better understand this dynamic environment so that developers can have greater confidence that they have picked the right site. So it's around de-risking the site selection. So this is a very collaborative piece of work. largely with Mark Collin, who until very recently was a research fellow in ICRAG. He's now with the School of Earth Sciences. And he has access to an enormous amount of repeat survey data for the Irish Sea and also the Yamet site in the West Coast. John and Saladin, who are down the back, a shout out to them, they're getting the flume operational in our school in civil engineering. And we're hopeful that this is going to provide some really great data, particularly for me, for validating some of the modeling work that I'm doing. So we had a master's student funded in this space, which was great, and they produced some excellent work. And we've recently got an SCAI or D&D grant. So there's a really exciting momentum behind this work. So we're actively looking for a postdoc and some PhD students on this project. So it's another little pitch to the audience if you've an appetite or an interest in that space. We're also, a shameless pitch, having conversations around the strategic priorities call that the Earth Institute run, with the loose kind of theme of a seafloor research group. So again, if you've got an interest or an appetite and you'd like to talk to us, please do reach out. So I'm just going to much more briefly mention the other two pieces of work that I'm involved with. And this is where I'm a collaborator. I'm not leading these, but this is around optimizing wastewater treatment processes. So when we look at the wastewater treatment tanks or facilities, there's always a risk around dead zones, short-circuiting, clogging, whereby regions of the tank are just very stagnant, and where there's a stagnation region, then there isn't good quality water treatment happening. So the question is around, can we make these more efficient? Can we optimize their geometry, or the choice of media, or the installation of baffles to make the whole system more efficient? So this is very collaborative research. It's with Dr. Sarah Cottrell in civil engineering, and we're co-supervising a student, doing some modeling, doing some experiments, looking at this question, particularly around whether certain geometry of baffles, length of baffle, thickness of baffle, might create better flow dynamic conditions to improve the efficiency of this system. And then the last one is with Saladin, and this is around eco-engineering sea defenses. So the concerns that we all have around climate change, sea level rise, and coastal flooding, you will often see coastal sea defenses. These are sometimes large lumps of concrete or large rocks. And the idea here is that they take the energy out of the waves and reduce the impact on the coast. But they are often very problematic in terms of the disruption to the local ecosystems. So the idea is to develop eco-engineering sea defenses that are more environmentally friendly and more friendly to the local ecosystems. So this is work that we've only just very recently started. Myself and Saladin are supervising a student, looking at whether we can design, propose more environmentally friendly eco-defenses, perhaps the flower pot design, drilling holes, whether that type of idea might work. And we're intending on looking at this from, again, a mixture of computer modeling and experimental work in flumes. So yeah, I won't hold you from the tea and biscuits for too much longer. That's me. Please feel free to reach out and connect. I'd be delighted to hear from anyone. Thank you very much.